So it looks like we're just about ready. Y'all want to take a seat? Catch the last beer, which is over there in the cooler. Let's see if people do make a dash. Restrooms are behind me, you know, where you came in. Just keep walking in that direction a little bit. That's where the restrooms are, out that way. So, you know where the beer is, you know where the restrooms are. Anything else important? Well, welcome to yet another edition of the Bay Area Scala Enthusiasts Meetup. And thanks for Box for being here. It's all me tonight, pretty much, which makes me feel a little bit self-conscious, but we did take a poll, and we did almost everything of higher priority that left me. So yesterday, on the weekend, I put out another poll asking people to vote for what you would like to have as topics for upcoming meetings. And so far, before this, we had 14 people respond. So unless we get more respondents, those 14 people's opinions will rule. So I encourage all of you to, you should have gotten an email from BASE saying that there was a poll, and go there and vote on the opinions, the suggestions that have been put up there, or add your own, because we're using Google Moderator, I think it's called, and you're able to suggest your own topics, and you can comment on other people's topics, and you can vote, and so you really have the power to express yourself. And it would be great instead of having 14 people vote that we had 100 or a couple hundred. There's more than 500 people in this meetup, so just that have 14 people express an opinion isn't exactly a quorum. Let me know if you need the URL or something, but you should all have the email. All right, so we're gonna ask for announcements in a second, and the format of tonight is we'll do that, and then someone from Box will talk about Box itself as a company and how they use Scala, and then I'll give my talk. And this talk has been evolving for a while, so it has the potential to go on forever, but we're not going to do that. I have a demo part which I could give, or I could shorten, or I could cut it out, so it could be all talk or all code or somewhere in between. And I'll basically take my guidance from you. Then at the end, there's a giveaway, and it looks like we have enough. I have 2 copies of IntelliJ IDEA, fully loaded, to give away to individuals, 2 copies of JRebel, which is enabled for Scala and Java, and 2 copies of Artema's Actors book, Akka Actors book, and that's version 1.2 of Akka Actors, unfortunately. So we'll give all those away. Now, the first 2 prizes that we're going to give away are going to be people who tweet. The rest will be picked from a draw. Oh, it's not here. Hang on, let me fix that. Okay, so that hashtag, if you tweet something about what you hear tonight to the hashtag, we'll have someone, one of you people will be randomly picked as a judge, and they'll select 2 winners based on what you tweeted. And the other 4 prizes will be random draws. So if you've got something to say, presumably be positive, tweet it to that hashtag, AkkaFuture. So, announcements then. Does anybody have jobs that they're hiring for, or they're looking for a job, or you're new to this place, you've got something to say you want to share?
Hi guys, my name is Irfan Ahmed. I'm recently co-founded a company called Cloud Physics. There's a lot more to say about the company, but one thing I'll start with is to whet your appetite and talk to me afterwards. And my co-founder Jim is here to raise his hand. Jim. We are with our first few customers, for each customer, we get 1 billion samples per day of data. We expect to have 100,000 of these customers. So we need people like yourself to come and hopefully help us build that sort of a large scalable system.
And again, if you guys want to talk about things, go over to the bar area where it's good for hanging out and talk about, hey, I'll hire you, pay me $1 bazillion. No, I need $1 trillion. Any other announcements?
Hi everyone, my name is Horacio. I'm the executive director of Startup Chile. I'm not sure if you know about the program. We give 40K equity free for a 6-month period to live in Chile. And now we are looking for startups that are early stage, so probably here I can find more than if you have doubts about the program, just I'll be there after the meetup, so you can join me and ask me every question that you can have.
Other announcements? Just 2? Oh, come on. There must be more going on than that. No? Okay. Well, in that case, let's move on to our next portion here. Who from Box would like to talk about what's happening?
Hi everybody, thanks for being here. So I'm Antoine from Box. I work in the storage team at Box, and we actually do a lot of Scala at Box, and we are hiring. So you know what to do at the end of the time. Okay, thank you.
You want to say something about
Yeah, so just a quick context around Scala at Box. We used to be a pure LAMP architecture, so PHP, MySQL. And about 1 year ago, we decided to move to the JVM, mainly for performance reasons, and we wanted to use a statically typed language. So we hesitated between, I think, Java, Scala, and Clojure, and we decided on Scala because it's more fun to code. And yeah, basically that was the main reason. So we have projects around, for example, real time. So on Box, when you collaborate files with other users, you can see real-time updates like this, and we use Scala to do that. It's our project. In storage, we also use Scala to do pretty much anything related to I/O right now, and we have several projects doing that. And we also use Scala for our testing infrastructure. Do you want to say something? Yeah.
So we have a front end over Selenium that we built using Scala. We also use it in our test case management system and in our test data extraction and reporting system. So those are the original uses of Scala, and it's spread from my group to the backend people.
Thank you. Yes, so as a conclusion, we really like Scala. We have many new projects written in Scala. And so we are really excited to have more people coming in and that want to write Scala. Thank you.
And you want to talk to those guys, just wander over there, and we'll assume that if you're wandering in that direction, you want to talk to somebody about work, right? So you'll all just suddenly shift in that direction. This microphone is for questions. If you have a question, I won't talk to you or listen to you unless you use the microphone, and I'm going to put it here. It has 2 on buttons. One of them's turned off. So slide them both so they both say on. And speak your mind and we'll deal with it. So feel free to interrupt, that's fine. But I do want to interrupt with a microphone. Okay. Oh, and this is Google Moderator. This is actually where you can vote for things. Right now, Play 2 is in the winning slot here. And you can see that someone put suggestions as to 2 subtopics about Play, and I thought they were great. This is a ridiculous URL, but it should be in your inbox, like I said. That's Half Moon Bay in the background where I live. No. I wish. Okay. So this talk grew out of a book that I wrote, and and there's a picture of it, Composable Futures with Akka 2.0. This book is for Java programmers as well as Scala programmers. But tonight, I'm going to focus on the Scala side. I can talk about Java, but that wasn't my intention when I started. But if you have Java questions, I'll be happy to address them. Okay, so the outline of the talk is I'm going to review concurrency in general. And concurrency in this case is Java concurrency. And then I'm going to talk about what Akka brings to the table and what Scala brings to the table. And the intention was to whiz quickly through Java 101 concurrency. However, there's actually a lot more, unless you've been hardcore writing concurrency in Java for some time, since JDK 1.5 or later, there may be things that you have not quite come to grips with yet. So let me know at the appropriate time and I can go into more detail. Then I'm going to give some definitions, just 2 definitions, but they're important, and that will be used afterwards, all the rest of the talk. And we'll talk about 5 concurrency options plus a love child. Originally, I had only talked about the 5, and then I thought, well, the love child almost deserves special billing. And there's actually this other one, the love grandchild, but I'm not sure I'm ready to admit to it yet. So if you're interested in the book, about half of what I'm going to talk about tonight is in the book. The other half is in the book that is yet to come, the love book. Yeah? So about myself, I'm a contractor, and I run this microeconomics research contract software place, and I'm a hands-on guy. I write code every day. I do training and mentoring, and sometimes I'll act as an interim VP engineering for startups or bigger companies that are in transition, and VP suddenly got thrown out the door and they need somebody. I also do a fair percentage of my work as a software expert. I'm actually working on 2 cases now for US federal court where there's some IP litigation going on, something to do with software. I have particular interest in artificial personality, so one day I hope to start a company based on that, launch a product line. I've got some code I've been working on for several years. And of course I organized this group as well as a co-organized Scala for startups in San Francisco. Okay, so into the talk now. This slide sets us up for the whole talk. So it's a historical thing. I stole this slide from Martin Odersky. So if you saw his, I think it was December presentation, he used this early in his talk as well. So what we have historically here at the top is clock rate, number of transistors. And you can see it's roughly following Moore's law. This is a semi-log scale, so the vertical axis has been compressed. It seems linear, therefore. And we haven't hit the physical limits, but within 10 years we probably will. Right now we're using silicon, we're probably going to continue using silicon. If we were using germanium or diamond or sapphire or something more exotic, we could push this up some ways, and we could also push up the frequency of the clock much higher, but that would be at a much greater cost. So instead what happened is around 2003, clock rate plateaued. And instead of using more transistors to make things go faster and making dimensions even smaller, since 2003 what you've seen is that the number of cores has increased. So this has an Intel i7, this laptop. It has 4 CPUs, and every CPU has 2 hardware-threaded hardware implementations of threading. This has 2 CPUs, this little phone. I bet you in 10 years, this will have 50 CPUs. This may have 1,000 CPUs. That's just the way things are going. And so my message to you is, if you don't know how to take advantage of multiple cores effectively, you're stuck in 2003. So Java doesn't help you out much here. It's very difficult to work effectively with many cores. And so this is the motivation for why do we care about concurrency. So every core can be running 1 thread at a time, and you just jump between threads very quickly, and it seems like many things are happening simultaneously. You know this. With more cores, you could just do that better. So as you know, threads are scheduled by an operating system. They're actually hardware resources. and they require software support. So it's almost like a thread is a tangible thing, where it's actually a, an emergent property of the CPU. It's expensive to create a thread, and so when you have a thread, you don't normally want to throw it away when you're finished. You want to put it back somewhere. The next time you need another thread, you can pick it up. So that's the idea of pooling. You know this already. Now the problem we have with threads is you have many threads all trying to interact with the same data, that the hardware of the machine gets in your way. And each CPU will see a different view of the data, and that data can get out of sync between the CPUs. I have a picture for this in a minute. So this is a completely boring slide for you. You've seen this years ago. These people were back in first year university. But all I want to show you is that we've got a main routine. It spawns a couple of threads. One of those threads spawns another thread. The main routine has ended here. We have executed from top to bottom. We stop. And the other threads keep on going until they're finished, until finally the whole thing can end. So this actually happens in Akka. You launch a process, have some futures running, and then you wonder why your program doesn't exit. Because you still got some threads running, and you have to shut down your thread pool before your program can exit. So one of the first things you discover. So the standard thread pools that Java gives you are also used in Scala, and they're also used in Akka. So everything you know about threading still is useful for you. Now, actually, the standard thread pools given to you in JDK 5 and 6 include a cached pool. So you have here a cached thread pool is useful in the case where you want to minimize the overhead at any one moment consumed by your program. In this case, your thread pool, if you have a thread that isn't used for long enough, the thread is actually discarded. And so you have fewer and fewer threads in the pool if you don't use them. Conversely, if you need another thread, it will be added to the pool and created. And so this thing, you can set the timeout, and the idea is that you're going to reduce the amount of threads consumed by your program. If, on the other hand, you have a program that needs to instant on, you have a task that arrives, bam, assign it to a thread, run it right away. You don't want that kind of an algorithm. You want instead a fixed thread pool where you allocate the maximum you're ever going to use. The overhead is always taken up, and you can just assign it straight away. You don't have to ever wait. Now, Akka doesn't use a scheduled thread pool. You can write a program that uses this type of thread pool. Instead, Akka uses something that, it's a hash wheel timer, which is defined in Netty, and it tries to minimize resource consumption. It's very inaccurate. So if you want to have a timer that is accurate, then you should use either a different thread pool or just set up a timer thread, because they're simple to do, and they'll be pretty accurate. So it's a trade-off. So a single thread pool is maybe good for testing, just to see what race conditions might show up, but in production I don't see them used very often. There are some situations, generally not. JDK 7, however, brought in fork join. That was one of the big changes for JDK 7. And fork join is a new kind of thread pool that's kind of smart. And it's good for JDK 7's idea is you have a task that can be subdivided. Maybe it is a recursive task. Maybe it is just easily chunked by nature. And so for those kinds of problems, fork join is an adaptive kind of algorithm. It has more overhead than all of the other algorithms I've told you about, significantly more. But unless your tasks are very, very short-lived, then the overhead won't be noticeable. If you do have tons of just little bitty things, you're probably better off with fixed or cache. However, fork join is the default for for the Akka thread pool. And so if you look at your load and think, we're just not getting the throughput we expected, and it turns out that the kind of computations you're doing are just the tiny little small features, and and lots of them, then you're just using the wrong thread pool. Yes, sir. How do you turn on the mic? Go ahead.
So, with fork join, and what's the difference between the completion service executor? So if you're using a completion service executor, you do the same, you actually get the same thing, right?
Which executor?
It's completion service executor. So basically, you're submitted to the executor to the completion service, in which each job, for whatever job finished, get returned, you get a set of futures. So essentially the same thing like fork join. In fork join, you just gave a bunch of them all together.
I think completion service is actually a layer above. If I remember correct. I think it's actually built out of it. I could be wrong, but I think there's a relationship between them.
The completion service in 1.6, and the JDK 6.
I don't know.
That's the one we always use.
Okay, don't know. I'm not here to bullshit you. So one thing I wanted to say was JSR 166Y, which is JDK 7 fork join, is available for JDK 6. And so this is what Akka does. It bundles JSR 166 inside. And so if you're using JDK 6, you have fork join available. But it is the, depending on the version of Akka you have, if you stay current, this is not a problem. If you had an original version like Akka 1.2, you were using the original version of JSR 166Y. It was updated. It had some bugs fixed. It got better. So if you're just riding with the current wave, I expect we'll see further revisions. Doug Lee is very busy here. And you don't have to switch to JDK 7 because you've got it available. Oh, the other thing I wanted to say is you can write your own thread pool. And they're easy to write. They're just very difficult to test. So I've written my own, but I'm scared to death to use it. I'm pretty confident in what I wrote, but the bugs are insidious, and Murphy says it will hurt you at the worst time in the worst way. So you're better off, if you need something special, to use Akka's configuration utility. Here what we are doing, normally, I guess I'm getting ahead of myself, I actually have a slide about this. Here's my definitions, just two. So if you're a C programmer, you probably don't agree with these definitions. I don't care. We're going to use these definitions for this talk. Just understand what I mean when I say these words, and you can disagree with me, that's fine. If you come from a functional programming background, you probably will agree, and we won't argue. But anyway, just for clarity, for the purpose of this talk, you don't have to agree, but concurrent tasks, I will say, are stateful and have complex interactions. But parallelizable tasks are stateless and don't interact, and they're composable. So I'm going to give you some concrete examples and as we move along. So when I say parallelizable, I mean that this thread runs by itself from start to end and doesn't talk to other threads while it's doing that. Whereas if I say concurrency, I mean we have all these guys in a milieu, they're just, a mosh pit. So java.util.concurrent is the basis for all of Scala and Akka's concurrency, parallelization, all the multitasking. And they're all built out of callables. If you remember, a callable is a class. And so every time that you have a thread running a callable, you have a separate class required. And so if you have many things happening, you probably have many types of classes. And so a closure in Scala turns into a Lambda class. And it's possible in some scenarios you have a whole lot more classes than you would expect. That's just one of the outcomes of this. So a thread pool is a collection of threads. It's managed by an executor. Often people use these two words as synonyms for each other. As if you could say, when I say executor, think thread pool manager, right? And inside the thread pool manager has got the thread pool. But often people just blur the distinction, and I will probably do that. If tonight I say executor, think thread pool manager, or maybe thread pool, or maybe Mike's not sure. Similarly, the other way, if you hear thread pool, think executor. So here's Java util concurrent on one slide. These are all the things I believe that exist in Java util concurrent for JDK 7. I'm not going to go through them all. I just list them here. So if you say, I know Java util concurrent, well, actually I don't spend so much time here. And there's a completion service and countdown latch. I've used that, but the things that you end up using a fair bit in Scala are callables and runnables, principal callables, actually, threads, thread pools, and executors. You don't normally need atomic because we have STM, we have other good things. You move beyond that. You don't normally need to worry about blocks. Concurrent collections can be handy and it might be worth your while to look into that. For example, did you know that Java supports a hash map where you can lock on a key value pair? So you can have different threads actually accessing each key value pair at the same time without any problem. Who knew that? And the rest of you didn't know that. And so that's a good thing to know about because concurrent collections are pretty cool. They don't have much of a penalty associated with them. Now, JDK futures are anemic, pointless, should not be used. They're not composable. It's an early attempt. Don't look at that. I don't look much at this stuff here either. So as I said, knowing your thread pools is important. Knowing all about, really getting to know what a callable is, being really familiar with callable is good. And concurrent collections are worth a look. See, that was my review, right? I could go into more detail about the things that I think are important if you want. But I assume that most of you have seen this already. Who wants more detail on what I just on that slide? Okay, I won't bore you. So I have an example for you about a multi-threaded program scenario where the average engineer says, I'm smarter than that. And I put forth, I posit that perhaps you are not. As I thought I was, and I was wrong. Well, maybe you're smarter than me, I don't know. But the main point is, non-determinism is your enemy. And you normally hear people say, if you access a shared mutable state, that's the problem between threads. So it would make sense logically that if you're all reading and writing one particular variable from many threads, that is going to be chaos. But did you also know that if you have shared state that's not mutable, everybody's reading their own variable and they're next to each other, that could be a problem? Yeah, well, let me show you. So first of all, let's talk about some hardware. You have, in a CPU, you have registers. There's very few of them, they go very quickly. They can, one clock cycle, you can do something. And then you have 3 levels of cache in modern processors. And depending on the model of the processor you have and the manufacturer, the caches may do slightly different, especially the L2 cache. So the first cache is the fastest, and the second cache is a little slower, the third level cache is slower, and so on. So here's a picture. This is a picture of the processor that's in this laptop. So it's an Intel i7-900 series. Actually, it's my desktop. This isn't the one. It looks the same though. So of the 4 cores, you have 2 threads, hardware threads. So it looks like 8 virtual cores. And each of these has got a level 1 instruction cache and data cache. And you have a level 2 cache, which is a mixture of instructions and data. Then you have a level 3 cache, which is just data. And then you have main memory. So let's say I have an array. I've got 8 elements in the array. I've got 8 threads, hardware threads. And I'm going to write a program where thread 0 reads A0, all the way down to thread 7 reads A7. And then they're going to do some computation, they're going to write the results back. All right? So I have a one-to-one mapping of threads to data elements. And thread 0 doesn't look at the rest of the array, and so on. Everybody's just focused on their one little element. It's worth noting that you've got about an order of magnitude difference each time you move over here. This is, to read this memory, could take several hundred clock cycles. You're running at whatever number of gigahertz over there, 2 point something, and it takes hundreds of cycles to read 1 bit of memory. But in fact, you never do read 1 byte of memory. You read what's called a cache line. So something that's going to fill a data or instruction cache. So this thing gets refilled as a unit. I mean, it requests, there's a minimum number of bytes it's going to request, and they're contiguous. So if you want to read this variable, it's actually going to read all of those and a bunch more. So it can load it into the cache. And so you want all these caches to have the same value, and if they don't, they're not coherent. And the L2 cache might be shared between these two, and the L3 cache is shared between everybody. And so the value in here, if people are reading and writing, if threads are reading and writing, and thread 0 has changed this value, and thread 7 wants to read that value. Well, what happens is that when thread 0 writes this value out, there's this protocol called messy. Oops. Okay, I'm getting ahead of myself. I'll get back. Modified, exclusive, shared, invalid. That's the states of things that are in your cache line. And so when one core writes, the other cores will be notified, oh, by the way, the thing you're looking at is out of date now. So let's just go back a bit. Let's talk about latencies just a second, so we can get a sense of how slow things really are compared to these caches. Now, a lot of this stuff is, if you Google latency, you'll find this is stolen from them. I just added a little bit here and there. So an L1 cache reference from the CPU takes half a nanosecond. It's pretty fast. That's why they're there, but they're very small. To execute an instruction might take 1 nanosecond. Now, if you know that electricity travels 1 foot in a nanosecond, you can imagine then what's happened is that those little electrons have basically whizzed around the equivalent of about 1 foot's worth of copper or whatever. Actually, it didn't, because the PNP boundaries have them going, trickling a little slower, but they actually did move a fair distance. If in the speculative execution branch, sometimes if it had guessed, oh, you're going to branch and you did it, things slowed down. Well, that's pretty small. But look, to access the L2 cache, it's 7 nanoseconds. That's 14 times slower than the L1 cache. It's about an order of magnitude, right? Mutex, they're done obviously in L2s because if you want to lock or unlock a mutex, it takes 25 nanoseconds. You're not going to make memory for that. And so, if you have a mutex and it becomes invalid because somebody flushed their cache line, then suddenly you change your mutex access goes from 25 nanoseconds down to 100 to 300 nanosecond, which means that your program goes a whole lot slower. So, if you're using mutexes for your programming, you might find that things are a lot less efficient than you thought. Okay, so L3 cache is 40 nanoseconds. In 1 microsecond, which is 1,000 nanoseconds, electricity travels about 1,000 feet, 984 feet. To send a message between Akka actors within the same JVM takes about a microsecond. Plus or minus, depending on lots of factors, but in the order of a microsecond. That's still pretty fast. And if you're using a zip to compress something, about 3 microseconds for 1 kbytes. In a gigabit Ethernet, to send 2,000 bytes, that's within a subnet. You might be talking 20 milliseconds. Well, maybe not the same subnet. Maybe there's a few hops involved. 20 is pretty slow, right? However, look at this SSD seek. That's 100 milliseconds. And you thought they were so fast. But they're not. Compared to all the other things we've talked about, that's incredibly slow. SSDs. I mean, that's nuts. To read a megabyte of RAM, this is from main memory, into, say, L3 cache, that's a fair bit of time. Now, here's something I found, and this actually becomes pretty important when you're trying to figure out how long does stuff take, and we'll learn about this in actors. When I talk about actors, I want to anchor this for you now. I had a custom data structure which had in it 3 hash maps. They had some fanciness to them, and it took a whole lot of time. The first time I stuck data into them, they weren't that big. Maybe I was moving less than a K of memory into them. But look, that's almost 480 milliseconds the first time. The second time I did it, microseconds. The second time it took 5. Oh, yeah, we should have some more zeros here. I should be talking milliseconds. In fact, thanks for catching the error from the room. I have another slide where things are even slower. It takes a whole lot of time. The second time, it only takes 5 milliseconds. Okay, so just to finish off, disk seeks, they're just so fast, right? This is a pretty fast disk. And to send a packet between California, Europe, and back takes forever. So if you're just thinking about, I'm a computer scientist, I don't worry about hardware at all, you're being naive, because you've got to think about how long things take, and if it's local or not, and so on. So the point of all of this was to say, back to my array here, I have 8 little values, and this problem is called cache line ping pong. Just have an array, and if I dedicate one thread to each of those array elements, you would expect that the speed increases. This is a speed increase. It's kind of weird, but it's the opposite of the way I would normally think. You add you double the number of CPUs from 1 to 2, you expect things to go twice as fast. And if you add 4 CPUs, they should be 4 times as fast, and so on. You're expecting a linear speed increase. But in fact, what will happen is you write it the way where each thread writes to the memory itself. You get a decrease, and you get about 8% of the throughput that you expect. So it has to do with the block sizes. Because messy protocol says when each CPU wants to read some data, that it's not going to read 1 byte of data, it's going to read a chunk, and that chunk depends on the processor manufacturer and the model. And so what happens is that chunk, when you write to it, invalidates everybody else's, and you've got some thrashing going on. I've seen this before. So this is true whether you are sharing state or not. Just the fact that your data values are next to each other, close enough, that the CPUs are actually affecting each other. And so what that means is that directly writing your answer from a thread to main memory is just wrong. That in itself is an error. I admit, you hadn't heard that before. So here's one solution, the java.util.concurrent solution. Well, you'd mark your data array volatile, and what that means is that every time you access it and you write a value, it causes L3 cache, the L2 cache, the L1 cache, all to flush for that memory segment, that cache line, which means that it slows things down for all of the other CPUs. That doesn't actually solve the problem. And then you also could mark it synchronized, access synchronized, which says I'm only running 1 thread at a time. So that solves the problem, all right? But you're running with 1 thread much slower, so that's not a good solution. So a better solution is not to write directly back to your array right away. Instead, I'm de-emphasizing the importance of shared mutable state. I'm saying if there's mutable state accessed from a thread, that in itself is a problem. So the real solution is to use more functional programming techniques. Prismatic has some guidelines on that. And it's pretty common sense. Build things small, little flexible units, compose them together. I'll define the composition in a second. And instead of thinking Hadoop is the answer for all my problems, it's a big lumbering monster. You could, and the frameworks themselves aren't your answer either. Having maybe a library of routines where you can build just little pieces as you need, and putting it together are more likely to give you a good result. So here's where I define what I meant by composition. And this is stuff you should already know. So in Unix, or Linux, or Xenix, or HPUX, or you name it, you've got pipes. You've all used pipes before. This is nothing new to you. And so you've got a data store. You run it through some kind of a process or transformation. And in between each of these transformation verbs, you end up having a temporary data structure. And so this just gets listed, so nothing's really changed. Then it gets sorted, and then we remove the duplicates, and then we chop off the front part, and you end up with the same data as before, but it's been rearranged and massaged and transformed. And so that's just how composition works. You have a bunch of actions that are, one after the other, each one reading the result of the previous, and you have temporary data. This is functional programming, actually. I mean, it's kind of like functional programming. You haven't changed the original data, and this data doesn't interact with that data. This data turns into that data, which turns into that data. It's just like functional programming. So there's no magic to composition then. It's just putting a bunch of transformations together. Same thing in parallel. Now we're going to do this with Akka or Scala parallel collections. You can have a bunch of things that happen all together. So you have an original data source, which is then chunked. So you take a piece of it and you send it over here, another piece you send it over here, map it together, reduce them together, and then you've got the result. Same idea, use composition. So hopefully there's no mystery about that. Here are the 5 options plus the love child that you have available to you if you're a Scala programmer and you're using Akka. Java.util.concurrent is all there, and you can still use it and abuse it to your heart's content. I suggest that you maybe just know that it's there and understand how executors work, because that's important, and instead use these higher level constructs for everything else. So Scala parallel collections are the easiest way to get concurrency without any real effort on your part. You don't have to learn any new concepts, they just work. That's a wonderful thing. Akka Futures are the next level. They are very similar to Scala parallel collections. Both of these things offer you little containers that threads pick up, and they do their bit, and the result is passed along. So both Scala parallel collections and Akka Futures act as containers for callables. There's a place for a callable to be while it's been assigned a thread, and so work gets done. So Akka Futures and Scala parallel collections can both be they can both be composed. Akka Futures have more options; they're more complex. The next level of things is dataflow, and we'll talk about that. The glue. I think of Akka dataflow as glue. So Scala parallel collections require Scala. Can't be used from Java. Akka Futures, you have the choice. You can use them from Java or Scala. Some operations get pretty wild in Java. It makes sense if you have a Java program and you want to do some work in Futures. Maybe you're going to introduce a little bit of Java, Scala code and call the Scala from Java. That's simple to do, works well. The next level is agents. And that is kind of a mixture between actors, but actors are inside, so you don't see them. And something called STM, software transactional memory. And you can mix and match all of these things together. And then you have Akka actors, which I have opinions on. I'll be not shy in sharing it with you. So this book here on holistic logging is to let you know that Scala parallel collections, futures, and dataflow are all covered in that book. It doesn't cover agents, it doesn't cover actors. I have an article in InfoCube that came out April 23rd, and it helps you with some benchmarking concepts for Scala parallel collections and futures. So just to talk about parallel collections now, they're not configurable, they just work. So they traded off simplicity for ease of use, and they're blocking. So you might think, well, blocking is bad, right? Isn't that always bad? it's not. Here's a scenario. Let's say I'm writing a simulation. And simulations are generally written, you have a clock ticking. And a bunch of things happen, and then the clock ticks again. Things happen again. So the result of the last tick is fed into the next tick. And in between each tick, you can pull the results. During a tick, the results are not available. Ticks are therefore short, and so that you just run this thing as fast as you can. And so weather works this way, weather simulation works this way, modeling fusion in suns is done this way. All kinds of things are modeled. If you were going to model millions of monkeys or infinite number of monkeys typing randomly to recreate the verse of Shakespeare, you would do that this way. And for every clock tick, you would basically say, and this is my monkeys here. You have an entropy generator. It's putting out a whole lot of random keystrokes every clock tick. And then you compare that to some part of the manuscript that you made it to. And you just reduce this down. You pick the monkey who's best. And say, my simulation has gotten 10 pages into the document. Simulations generally look like this. In Scala parallel collections, you basically say, this is assigned one thread, and this is another thread, and that's another thread. You would write a callable in Java if you wanted it to be callable, and it would have all this in it, and the result that it returns would be available, and it actually gets put in the, it's called a Scala parallel collection. So basically, you drop in a callable, and you get a result at the end of the computation. So every clock tick, your callable will happen, and you'll extract one more value in parallel from the whole collection. So the fact that this is blocking is just fine for simulation. It's not a problem. In fact, that's what you need. If you were going to try to program this in actors and to be able to retrieve intermediate results, and it was a nightmare, it gets really complicated. So Scala parallel collections are the way to go for that sort of thing. They're backed up with fork join pools. So in the case of this infinite number of monkeys, it turns out that that kind of an algorithm is a natural fit for a fork join because it's chunkable, it's recursive, and they're easy to reason with. So if you want to understand, does my program work? You're looking for bugs. This program, you're going to get it working really fast. It's going to be short. It's going to do the job. It's going to be efficient. So hooray for Scala parallel collections. You can tell I like these things. Okay, yes?
So on the parallel collections, which collections?
I'm afraid I can't hear you.
So which collections have a parallel equivalent? Is it all of them? And is the following?
Yes, all you have to do is put .par at the end of your collection, and you get the parallel equivalent. And another thing you can do is you can just declare it parallel. There is I don't know if I can remember the proper name, but let's say there's a hash map. There'll be a hash map par or the par hash map. But in any collection in Scala, if you then just .par it, will be a parallel equivalent.
When would you not want to do that? Is there overhead associated with it that's significant?
There is overhead. If you wanted to, whenever you talk about design of a multi-threaded system, there's never a simple answer. The fact that you are using a thread pool, the thread pool that this uses is the main thread pool of the program. You can't assign it another thread pool. So if your main program is doing something else with its default thread pool, then if this turned out to be a heavy load, you couldn't shift it off somewhere else to some other thread pool and tweak it in some way, like for example. There also are some, by making it a parallel collection, some of the methods that are able to change in nature slightly. Some actually go away, some new ones come in. So it does change things a little bit in terms of your flow. But conceptually, all that's happening is that if you have, now this is useful when you have a number of callables. If you just want to hold flat data, I mean just plain data types, there's no benefit for using parallel collections. It's when you have an array of callables you want to throw data at, and then have an array of results, then this might be very interesting. Any other questions? I have source code on this on the InfoQ article. You can see I wrote two benchmarks. One was IO bound, the other one was compute bound. So the compute bound one was pi to 1,000,000 decimal places, and IO bound simulated a web crawler where it had a variable delay. I just made thread go to sleep for a little while, pretending that it's crawling. And then you could see how these two different types of concurrency containers behaved with different loads and with different tweaks, different parameters. So more threads, less threads, different other settings for the threads. And it gives you a graphical response. And maybe I have that here. So you can see that the choice of threading model and container can make a big difference for the same program. I'll get to that later. Okay, may I move on? So Akka and java.util.concurrent, the point of this slide is to say java.util.concurrent is the basis for everything. And your application can use java.util.concurrent directly. It can also use Akka Futures directly, and it can use Akka Actors directly, all three, or none, or whatever mixture you like, it's up to you, okay? This is not to imply that this is better than that, but it does imply that there is an interaction between these two. You can pipe a future to an actor. So first of all, if you're going to use Akka, you need to know that there is a thing called the runtime, which they call the actor system, which is very unfortunate. It would be better if it was called the Akka system, because the actor system is required for everything you do with Akka. So it's not just for actors. It's the runtime support. It's heavyweight. You can have multiple of these things. They take a long time to start up. You can see the thing start up. You can almost see the lights dimming as it starts up. Okay? It's very configurable. You can have a lot of them running. But don't be starting them and stopping them all over the place. You're never going to get any work done. So the actor system has in it an analog to what you have in Java. So in Java you have executors. So this is your thread pool manager. And you have this whole hierarchy of classes that manage threads. But in the end you get some threads out which can back a future. Every future needs a thread to do anything. That's kind of fundamental to futures. And in fact, that's true for any concurrency. Without a thread, nothing happens. And Akka gives you a parallel stack. They use different words, but they do the same thing. So execution context down there is kind of, sort of like an executor. And anyway, so that's basically you get threads out. Now what's nice is with the Akka version of futures and the version that will be in Scala 2.10, you can either feed it a thread from java.util.concurrent or from actor system. And it will be the same thread and it will work the same way. And so if you already have some reason that you want to use this thread pool over here, you've been using it for a while, fine, use it. If you want to go and use this for whatever reason, and there are reasons, fine, go and use it. Doesn't matter. Once it's got its thread, it's happy. They're both equally easy to work with. You had a question?
Yeah, can you just define future?
Oh yeah, I will, but not yet. It's coming. Okay, so I wanted to talk about the actor system configuration. Actually, TypeSafe has this configuration utility that they use in all their software, and it's worth getting to know. And it's actually a big benefit to whether you're using the concurrency stuff or something else. So they have here in the Akka runtime, the actor system, there is embedded this file, reference.conf. It has all the default settings. It's always there. You can ignore it if you choose to, but by default, you get it. And if you have in your application, in a place like, oh, I don't know, Scala main resources, you put a file called application.conf, or it might be in Java main resources, or it might be in Scala test resources, or it could be in Java test resources, wherever you want to put it. This overlays that. So any settings that have the same key as you would have in the reference conf, well, the value specified in the application squashes whatever was there and trumps it. So you get a nice layering effect. If you're a library writer, and I've had to do this, then you want to take the default values, put in some extra values perhaps, then application values, and then maybe some overrides. And you can stack these as deep as you want. And the code to do that, I'll just show you here. Here I have a string, the first line. And it just sets the logging level to debug. And then I tell config factory, which is the type-safe configuration utility, to parse that string, and you get a configuration object. And now I also want to say, read the application conf file, and parse it, and make a configuration object. And then load the library conf file, do the same, parse it, and give me a configuration object. And then this says, load the default, which is reference.conf. Now we can just stir well. We can say config factory, load the string, which is the top level stuff, with fallback. Now this is an unfortunate name, with fallback, because to my mind, when you're falling back, it means you tried something, it didn't work, you're going to fall back to the alternative. That's not what this is doing. This is counterintuitive. What this is doing is actually overlaying the string, the top, with this, on top of this, on top of that, just like in the diagram here. And so what you get is any values that were specified here that are overridden there will be wiped out. You can add new values here. You can add more values here, and you can override any values that were below it, and so on. And so that's not what I would think of as a fallback, but that's what they wrote. And so for me, this was a conceptual hurdle I had to get over. That I think that's a poorly named method. So we've got a layering. So why do we care? I was talking about threads a second ago. Well, let's say you've got an application and it wants to run on the server, and the server has got a certain configuration. You're using a CPU, it's got, maybe it's an AMD, it was an Opteron, it was hot in its day, and realize you need something more modern. And so you're going to go to an Intel chip, maybe some of the latest Xeon or whatever. And you know that because the cache configurations between these two are so different, you're going to have to recharacterize your app. And so you benchmark your app, and you figure out the right kinds of thread pool configuration for it, the right parameters. If you're going to run this through a normal QA process, you're going to try things, you're going to have the original programmer write some code and hard code in all those values and all that information. And it's going to go through QA, and then they're going to say, on the test system it didn't work. And now you're going to change your program all over the place. You can't ship the program, the same program that the programmer wrote, and get it all the way through QA and deploy it. It just can't be done. However, with this, you can. With the type-safe utility, config utility, the thread pool manager is actually configured from the combination of all of these, configuration things. You can specify the thread pool you want, all the parameters for the thread pool, different things. And this can be done you can swap this one out at deployment time. Maybe this one's hard-coded in the library, and this is part of Akka, and then you could have some little like runtime tweak facility as well. So that's, for me, a big plus and a big reason to use the Akka system configuration utility, so use their thread pools instead of trying to write your own thread pool for your own special need. So I want a daemon thread with so many minimum, and I want to have a high threshold and all these crazy parameters. They kind of thought of them all, and so you don't have to think about writing any more thread pool executors. And what you write is what gets deployed and can be tested and benchmarked without going through another QA cycle. So that's a wonderful thing. Questions on that? Okay, so what's the future? So it's, I think I have a definition. Here, what is a feature? It's a holder for a result that will be available at a future time. So if I have a web crawler and I want to go and find out, I want to parse the value of a file. So I spin up a thread and I assign it a callable, and that's my feature. So the thread, the feature has got a callable assigned to it. It's got the thread assigned to it, and it will hold the result when the contents of that web file come back. That will be the result of the future. If there's an exception, that will be the result of the future. So the future is an either, and either can have one of two values. An either is actually a class. It can have a regular result, or it can have a throwable, and you can find out what it is. So when the result, basically, you spin up this thread, you give it the future, you assign it the callable, and then you just wait. You can either block for a result, or you can have a callback happen. So future does all of these things. And then you can take the result of that, and you can pipe it to the next activity, because it's composable. Futures are write once. So you can't change the value. Once it's got a value, that's the only value it's ever going to have. And that's insidious, because sometimes it can get confused in the version of backup that we have. SIP14, which will be a manifest in Scala 2.10, takes care of that. You should not be confused anymore. Go ahead.
So I remember last time when Twitter was presenting their features, so their features are different from Akka's feature.
Yes, somewhat.
So can you show us an example, the three features, the Java feature, the Twitter feature, and Akka feature, and see how they differ in code?
No, I can't do that, but I can talk to you. Okay. Now, you were there for the presentation when Marius, Erickson, and I were both talking about. So you've heard this already. You want to see code instead. I have. Okay. So Marius at the end of this presentation showed you a code example of Twitter features doing something, and I rewrote that same example for Akka features, and I have it with me. So if we don't get to it, I will be able to share that to you. But
or maybe just show the Akka feature compared to Java feature.
Java feature is not composable. That's the big thing. It is a container. It does hold a callable. You get a result back. The end. And so you can't do functional programming with it. So it's of limited interest, because that's only the beginning of the story of why this is cool and useful and scalable. But Java features don't let you do any more than that. Maybe in JDK 8 or 9 or whatever, we'll have more. But right now, JDK 7 is not composable. That's the big thing. So, okay. So features can be called from Java and Scala, like I said before. They're more flexible than Scala parallel collections. They don't block unless you want them to. By default, they don't block. They're not very complicated compared to some other options that you might be all hot to try, like actors. They're easy to reason about. So these callables are often referred to as payloads. If you want to get the proper benefit and have no errors, you should not have side effects. Okay, printlns, that's all right. You're allowed to do printlns. But if you're thinking functionally, you have a method that takes an input, produces an output, and that's all it does. If it's going messing around with global states somewhere, then you can't call that thing over and over and always get the same result. It's not idempotent. So that would mean that it should not be composed. And so, although it's possible to do that with features, it's very bad and will hurt you. So don't be thinking that, oh, well, how is it that I can get my features to interact with this global state? You probably don't want to do that. Now, the exception would be you have a static data structure that's initialized at the beginning of the program. It's constant all the way through. It's fine. You may read that, but just don't do any writing. So the Akka features we have in 2.02, which is current, and Scala 2.10's features, also known as SIP 14, help you manage concurrency in the sense of a parallel programming, not concurrency in the sense of many things happening all together with shared state. It's a higher level of primitives. And again, there, I need to say that once you've assigned a value, that's all you can do. You can't assign another value. So let's look at what some of the operations are. Here's all the operations that exist at this point. And this is a moving target. Those guys in Sweden, they work hard. They are always adding to this, and it's a challenge to keep up. So you have your standards, map and flat map. If you've been using Scala, you recognize these maybe from the list object. And it works just the same. So in this case, if you have one feature, you can put a transformation on it by calling map. And what map has a unique property is that it can take one type as an input and generate another type as an output. Most of the other transformations, well, flat map also has that. Other than map and flat map, if you get a T in, you're going to get a T out, or a list or a collection of T. But map and flat map are different. You could get something in and totally something else coming out, and that's what's useful. So if you have collections of features, they're also supported, and this is not available in Java, the Java features. So if I have a list of features, for example, let's say I had a whole lot of computation that was all done in parallel, and now I want to reduce that into a value. Then you have all these choices of fold, reduce, sequence, and traverse. Different flavors are pretty much the same thing, but they have some different properties. Like some of these will take, are more flexible in transforming a T into a U. Others need to have a T to a collection of T and they're more strict. Some of these have an initialization value and some don't. But they're all basically variations if you want to think of it as reduce. Right? So you've got map and reduce. You've often heard of map reduce. Well, these are the different flavors of reduce. Similarly, if you have collections of, you can do zip. You can run two features and you can take the first result that becomes available. So maybe you just launch a bunch of things. You can zip, 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 zips. It's a quick way of picking out the first answer and discarding the rest. Try and catch, finally, on complete, on failure, on success. This is helpful, but this is where you get into a bit of a, these don't change the feature's result. So when the feature runs, you've got a callback, and the callback could be on complete, on failure, or on success. And so on complete says whether it was failure or success, call this thing. However, if you think that at the end of on complete, you can return a value, you can't. Yeah, you can put a value to be returned. It will be ignored. Because what will be returned is the value of the feature. And if it failed, it will be the throwable that was passed in. And if it succeeded, it will be the value that was passed in. So in the on complete clause, you can do stuff. You can call a log or whatever, but you can't change what's coming out of it. So maybe you don't want to use that. Maybe if you have a failure, you might want to be able to call recover. So if your feature fetches a URL, if you get a, 500 or 400 series back from your HTTP server, you then say, let's call some other place. So recover can actually create a new feature. This is a feature that you create and use if the other feature didn't work. That's pretty helpful. Same idea with fallback to one case you have the feature pre-computed, ready to go, and the other one you basically just pass in another callable and you get that result. Flow is data flow. So data flow is initiated through a feature. And that's a very cool thing. I've got several slides on that. We'll just hold that for now. So these are all the things that you can do with features, and I managed to write a whole book on that, which seems remarkable. But you know, there's wrinkles and details. So Twitter uses composable futures for their stuff, and before they used Scala, they were running about 50 tweets a second. They were having fail whales. They're running on Ruby on Rails. And since they switched over to Scala Futures, they're running at 1,000 times greater load, about 50,000 tweets a second, plus gusts to higher numbers, and not so many fail whales. So Futures really can produce good results. They're easy to work with. You get some remarkable things going on. Cloud, when they switched from their LAMP stack, PHP and so on, to Play, and they went to Futures, so their load dropped in half. They can do all kinds more things. Okay, so just a little bit about some of the tuning things that are involved. I mentioned this before, and you can download this from GitHub, InfoQ's, the code that went with the InfoQ article. First of all, in a multitasking system, behavior is statistical in nature. So what we find is that you've got, well, this is actually a Gaussian distribution, which is probably not reasonable. But you'll find that there is a clustering of results. If you have a job that's done repeatedly, the value may always be the same, but the length of time it takes to do that might vary somewhat. And the variance could be a lot or it could be a little, and that depends on many things. If you tend to get the same, a tight clustering in the amount of time it takes, it's very repeatable, then your standard deviation is pretty small. And the standard deviation is like, if this is the kind of the middle mean, it's just how, I think that's about 90, but here it tells me 34.1% of the values will fall within this area. Here's another 34.1. So, you've got 68% of your values are within one standard deviation either way. So 2 standard deviation gets about 95% of all the values. And so the size of your standard deviation tells you how repeatable your computation is in terms of length of time it takes. So here at the end, I've put a little standard deviation picture. It's a Gaussian distribution, actually. And you can see that it's, hello? Okay. You can see that it's 2 standard deviations wide. So in other words, it takes at least 787 milliseconds to do this computation, plus maybe another 670 maybe, average being about 8,200 milliseconds or so. So in other words, if this blue is big, then you've got a lot of variance in how long it takes in computation. If the blue is small, it's kind of takes the same length of time. That's how to read that. And so we can see that it was, unfortunately my label was too long, but with this particular setup, it took a long time and it had a lot of variation. This setup took even longer, but it was very tightly clustered, so very repeatable. And so I'm comparing Scala parallel collections to the same computation to Akka Futures, just using different sorts of thread pools and tuning. So this is all published, and you can see that, and you can run the program and mess around with it. And I encourage you to actually consider taking this program and bringing it in-house and applying your own loads. If you want to deploy or test your setup and maximize your hardware, you should use the actual hardware, tricked out exactly the way you put it in production, and monitor it in this sort of a fashion. And then change one parameter at a time. As you graph these things, you'll see that which tunings make sense and make a difference. Otherwise, you're just guessing. And because you can make all these changes through configuration files, because Akka supports that, instead of recompiling your program every time. So you can actually pick out the right threading models and the right threading parameters. This is a real benefit. So you can measure that. Okay, so there's a lot that can be said about Scala, and so I can either now give you a live demo, or I can move on to more topics. So who wants a live demo on futures? We can do the live demo later too, but who wants the live demo later? Got it. I think you guys win, but not by much. Okay, I'm happy to do it now or later. It's really up to you. So I'll just stay with the flow, keep talking about things, and then we'll try it after. Dataflow, it's kind of a cool thing. Actually, it's blue. So if you have many threads all operating independently, and this is concurrency, it's not parallelism. You have a whole bunch of stuff, and they all need to interact, and that's just the nature of your problem. And try as you might, there's just no way to separate out the shared state. Then you might want to think about using dataflow, because dataflow is able to do this, and it's a very, very cool thing. Now, it only works with Scala, and it needs the limited continuations turned on. So you can't do this from Java. You can have Java kick it off, you can send the result back to Java, but Java just can't do this. And the other thing with dataflow is it looks like your typewriter threw up. It's got some funny operators. It's designed for working with shared mutable state. That's what it's for. So this is what you always wanted to do, and it's composable. So each block of code will have a result, and you can pipe that to the next thing. Sounds too good to be true, right? So here's an example. First of all, we start off, we create some promises. Now, a promise is, we talk about futures. Futures are placeholders. They're for the results of a computation when it becomes available. So if your program is the client, it makes a request to the server, which is maybe the executor, like the java.util.concurrent executor, and it receives you can think of it conceptually as it's the server, it receives the request, and it now creates a promise that it has to fulfill. And when the promise gets the value, that is passed back to the future, which then receives that value as the result. So this is the other half, this is the right side, W-R-I-T-E side of future. So we have 3 variables that will get a value at some point. Right now they don't have a value, they're unbound. This flow is future.flow. Okay, so I just wrote it as flow, but what I did was I imported future statically so that I could just write flow. But if I hadn't done that, I would have had to write future.flow. But I don't care whether it's a future or not. What matters is it is a flow block. So by writing this in an open squiggly, that creates a new thread. So this whole thing has a whole different thread context than outside. And this is an assignment. Okay, less than, that's equals, that's assignment. And so this X, which is the apply method in Scala, says, get me the value of X when it's available. But X doesn't have a value yet, so it blocks. Similarly, get me the value of Y when it's available. But it's not available, so it's really blocked. Anyway, whenever these two get values, it will be assigned to Z. And Z is also one of these special variables. And then that will unblock this, and we'll move to the next statement, and we'll print the result. Now, just reading down further, this is the end of that squiggly, so we're back in a normal thread context. We open up a new flow. This is running on another thread. So this is running on its own thread. That's running on its own thread. That's running on its own thread. This is running on its own thread. This is running on its own thread. This is running on its own thread. Got it? We've got threads everywhere. And what we do is we say, in this thread, assign X the value 40. Well, what happens as soon as that thread gets executed is that X is now bound to value. And this thread wakes up. I've got a value. Oh, but I'm still waiting for that. Okay, well, we're just going to block some more. And then this thread activates, and Y gets the value 2. Oh, look, we're waiting for the value 2. This thread unblocks. It adds 40 plus 2 gets the right answer, meaning the life, the universe, and everything. And the answer is 42, of course. And Z gets the value of 42. It prints out. That's pretty cool. Yes.
So the Z assignment in the first flow part, is that equivalent to the Java's cyclic area where you're waiting for the multiple thread to complete and then you assign results?
Which comparative?
In the second area.
Oh, cyclic barrier.
Yeah.
Yes, kind of, except that we're using Scala delimited continuations. So yes, but the but is, what happens here, this is a delimited continuation. In a continuation in Scala, your heap is used as a thread storage. So the whole context of the thread is stored on the heap, not the stack. And then later on, the same thread or another thread picks up that entire thread's state and resumes. That's not how Java works. And in fact, because Scala's delimited continuations are serializable, you could ship this whole computation to another network node and resume it there at any point, which is very cool. You could have checkpointing in your program. Save your state periodically, ship it off here, there, and everywhere. So anyway, that is the essence of a future. So if you needed to, you can call a future from, a data flow from an actor, from a future, from a regular piece of program. Doesn't matter, it's up to you. So if you needed to communicate and do something that's just so incredibly concurrent, this may be a good option for you. It's really easy to reason about this. It's obvious how things are working. Things block until they're ready. You can put in print statements and things kind of make sense. Unlike certain other things that we will soon come to. So I encourage you to think of data flow as a possible solution for your concurrency issues. So this is a slide I added to the deck over the weekend, and I wasn't really sure if I should bring this up or not, so I'm going to give it just a very light treatment. I wanted you to be aware that this stuff existed. STM, Scala transaction, it's software transaction memory. It's a way of sharing state between threads. It works on a wholly different premise than does future flow. Wholly different internals. And it has the characteristic that once you start using STM over here, it tends to invade the rest of your program. Okay? You have a ref, which is how you reference a piece of memory. And well, that ref means you need a ref over here. No, I need a ref over there. Next thing you've got refs everywhere. And maybe you don't want that. Anyway, the reason I'm introducing it is because it had an illegitimate child, a love child, with actors. And the result was something truly wonderful. So I want you to know that this is under the hood. There's a lot to know. I could, or someone could talk a lot about this particular topic, and the fact that I'm giving it such a light treatment is because we clearly don't have time for that. Anyway, I want to just let you know that this topic exists. So this is the love child here, agents. They are composable, and internally, they're built of actors and STM. But to use them, you would never know that actors were involved. And this is a good use of actors. So actors is this potentially very complicated and one of these things that could end up insidiously taking over your entire program. But it's also possible to write something with actors where the actors are completely internal and you never see them. And that is a very good thing. And all the stuff I've seen, like Blue Eyes, is written this way. And Play is written this way. There's actors inside, but you don't know them. You don't interact with them. And agents have them inside. It's a wonderful thing. So you send an agent a message, set the variable to 5. And this is a shared variable amongst many threads. And everybody can use it and write it, and there's no collision. You don't have a problem with caches becoming valid and so on. There's some extra dependencies in this case, instead of just a normal. By the way, this is build SBT. Who has never seen build SBT? Okay, so most of you have. Okay, so the quick answer then is your build file defines what your dependencies are and what versions you want. It's kind of like a Maven, POM, XML, except it's a lot less wordy. There, that's the quick answer. And so in addition to the normal actor, you also need an agent. And there's also transactors, but that's another story. So here's my example on agents. I do 2 imports. I create my actor system with all defaults. And I make 2 agents, and they're called 1 and 2. I guess I should have called them spy versus spy, huh? And they have values, 3 and 5. Now I want to compute a result. And so I say here in this for expression, basically unpack the value from agent 1 and add 1 to it and put that in the value of result. Very exciting, I know. And it gets more exciting. The point I'm trying to show you is that agent, this thing, which is a complicated little object, you can assign it in one thread, you can read it in another thread, you can reassign it in another thread. It never gets mixed up. You don't have issues. You can share your state through agents. And so in this case, if you want to get the value of an agent, you just type in get. And so by showing you the different operators, these are all the normal operators you would use. It looks just like any other piece of Scala. So agents are a very simple way of dealing with state that is shared and writable by many processes. Okay, so this is the final of the options, actors. This is the largest topic, and I will not attempt to go through all of actors. It's huge. The main principle is let it crash. So you have a computation, you give it to an actor, the actor maybe does the computation or delegates it to a subordinate actor that is supervising, or maybe a pool of actors that it's managing. And then if some of them die because they had some problem, that's okay, we can restart that computation or ignore it, but you get a resilient system this way. One of the biggest benefits of actors, if you want a distributed system, everything else I told you until this moment, everything happened in the same network node, in the same JVM. Actors are not restricted to one JVM. So, in other words, actors have an RPC mechanism. And they try to be independent of transport. Actors are cheap to create. They take 300 bytes. Whereas actor systems, the runtime, is a big lumbering thing. These guys, you can spin them up, think nothing about creating a feature, cheap. Think nothing about creating an actor. Think nothing about creating an agent. Think nothing about creating a threat, a dataflow variable. All of these things are really cheap. Threads are expensive, but they're pooled, they're managed. And the actor system runs all that. It's expensive too. But once you've paid that overhead, all this other stuff is cheap. Don't try to optimize the number of actors you have. Don't try to optimize the number of features you have. That's wrong thinking. These things are pennies. You don't even bother picking them up when you cross one on the road. They're that cheap. So actors are not composable. Oh, okay. So in fact, what you're doing is you're creating an operating system. You can be at that level of complexity. So if you are old enough, you would remember the days of Enterprise Java 2, and how EJB was the greatest thing ever. Everybody had to spend $40,000 to buy their copy of WebLogic. Fools. All they needed was a servlet, but they somehow thought they needed EJB. And so they used EJBs all over the place. Actors are getting the same sort of hype. Now, actors have been around 40 years, more than 40 years. This is not a new idea. And it is by far the most complex concurrency option. And therefore, it should be your last option. If you can't do this any other way, then think of actors. And there are proper places to use actors. But don't immediately think Akka equals actors. I've tried to say that in many ways tonight, and I'm just saying it again. One thing that's really nice about actors, and I've done this recently, you have some code, and you want to have some interaction with that code, with this other code, but they're really different code bases, and it would be so messy and painful to merge these code bases. Wouldn't it be nice to just send a message from here to there and back again? It's in the same JVM. In fact, it could be in two different class loader spaces. And actors are wonderful for that, because you don't get any pollution between your code bases, and yet they can interact. That's a wonderful thing. It's a good use case for actors. And it's simple. So actors are event-driven. And messages, which are sent between actors, could be anything. They can be strings, they can be objects, they can be whatever you want. If you have remote actors, then the messages have to be serializable. Kind of makes sense. And so in Scala, that means you would say with serializable on your declaration. Oh yeah, that was a reminder. The gotchas. Who here uses MongoDB? Not so many. Okay, I'll tell you just quickly. So Salat is a Scala wrapper around Casbah, which is the driver for MongoDB, and it likes case classes very much. And if you're trying to serialize something that isn't a case class, you can't. So if you have a data structure you need to serialize, it has to be a case class. But Scala has a bug that you can't have a case class that extends another case class. It won't compile. It's a known bug. It's been there for years. They're not going to fix it. It's too hard. So you just have to know that you cannot have a case class extend another case class. But you could have, say, a trait, which is extended by a case class. That's all right. You could have a class extended into a case class. That's okay too. You just can't have a case class extending another case class. Salat wants a case class. So for actors, you need to have things that are serializable. You want to send a message to a remote. So that means that Salat wants your message to be a case class. And if you have a hierarchy where you have of messages, where you have maybe some abstract base class and then you extend, they can be traits and so on, but nowhere can you have a case class in that hierarchy until you hit a leaf, because Scala will compile it. But it has to be a case class at the leaf, because Salat can't do it otherwise. So if you want to persist a message that is sent remotely, you'll come up with that realization. If you don't want to persist it through Mongo, that doesn't matter. But often, I just wrote something where this mattered a lot. And if I knew this at the beginning, I would say the week. So, actors run in packs. To say I wrote today a program that has one actor only in it, I'm bullshitting you, because it's just not doing anything. What is the sound of one hand clapping? I don't know. So you have hierarchies of actors, you have networks of actors, and you need to know queuing theory. Queuing theory. Turns out it's easy. Who can name a famous queuing theorist? Shout it out.
Erlang.
Oh, you listen to my talk. You're right, sir. Agner Krara Erlang from 100 years ago. We knew that already. So he developed queuing theory and traffic engineering for telephone network analysis. And Ericsson is backpedaling on this, but the language is called Erlang. It uses all these concepts. It's for this application, and the guy has the same name. So I think it makes sense that Erlang is, in fact, what's named after. Erlang is the definitive, the reference application for actors, really. Basically, they spawn a new actor for every request. Anything that needs doing, just make an actor and assign it to a unit of work. So whether you're making a web crawler, or you're handling incoming calls, or a switching system, you've got bazillions of actors that are cheap. You do the same thing in Scala. So there's different patterns. And I'm just going to walk you through some of the processes you might have to think about that you wouldn't have to think about otherwise. So imagine that we have, this is a thing that accepts work, right? If you want some work to be done, you send a message here with the description of the work. So this just handles the incoming load. Then you have this little chunker that takes that and breaks it down into smaller pieces, and then we throw it into this array of worker beads that grinds away at its chunk. And finally, they're all combined together, and then the answer is persisted. Okay? This is a standard kind of a pattern. It's not the only pattern, but it's one that you find a lot. Now, if you want to throw an unlimited amount of work at that first box, you'll find that your system chokes up eventually, somewhere. And so to have a mailbox to handle the incoming messages that is bounded means at some point it's going to get full. And if it's unbounded, means that your disk is going to get full. Something's going to break. So people talk about back pressure. So how is it that we can control the amount of work that we're accepting and just not accept anymore? Now, it's possible that you might want to say, well, for this incoming box, I'm just going to use flow control or HTTP or TCP's flow management. So I will allow my network to congest, and I'll let that, TCP's mechanisms handle my overflow for me. What that means is that all of your communication starts to degrade. Not a good solution. So what you need to do instead, perhaps, is you could also say, well, I'm going to have my workers request whenever they need another chunk of work, which will request up the line and say, okay, I'm ready for the next one. But then there's a delay, and you're not keeping your pipeline stoked. You want to optimize the amount of computation that's done in this CPU. And because CPUs have a cost, and so the idea is, given that we have a certain number of actors here, let's keep them, as many of them, busy most of the time. And keep the load factor high. So in that case, we'd like the workers just to be going all the time, because there's more of them than anything. And this chunker should have the next set ready to go. Anytime a worker says, I'm done, boom, gets hit with the next one. Shouldn't have time to think. And this guy should have something in its queue. So in other words, each of these has a mailbox of incoming work, and should have enough that it never empties, but not so much that it overflows. And that's the problem we're trying to solve, is management of your inbox. So there should be a standard mechanism for this in Scala. This is all too new, but I'm sure we'll find it. Here's some computations that you'll have to think of. This is queuing theory, and you're going to laugh at how simple it is. I'm going to say, to send a message from scanner to chunker is 10 milliseconds. You get the result back is 10 milliseconds. Boom, really fast. And the chunker has some work to do, and it's got some serialization to do that, because it's actually serializing a lot more data than this was in this fantasy that I have right now. So I gave it 35 milliseconds. And there might be an acknowledge back, which is 10 milliseconds. So it says, here's the word, got it, right? Ack-nack. So if you put an ack-nack all the way through, you have to account for the ack and the nack delay. So here's some work, got it. Here's some work, got it. We're done. So at the end of coming out of here, we might see 65 milliseconds. There's a lot of serialization that needs to be done. Now, maybe the workers have to think for a long time, 5,000 milliseconds, 5 seconds. So what you find here is that you just have to add up all the delays. You want to add this time and that time and this time and that time and this time. You get an idea of what is the maximum queue depth. So it's actually those two delays, this time, divided by the number of workers, tells you how big this queue has to be. At a minimum. So in this, if you follow that, you're in the ideal case, which never happens, you will have all that inbox empty to 0, and then fill up again. Empty to 0 and fill up again. Now it's not good to empty to 0. You should empty to something greater than 0, because there's a chance of underrun. But you get to see that as you add more workers, you need a bigger inbox. right? Because as the workers finish, they're going to just pull a bigger swath of work out. And similarly over here. So it's just a matter of balancing. And by having ACK and NACK all the way through, you can apply back pressure. So when this thing starts up, the scanner will say, well, I know that downstream I have so many workers, and I know that I will need at least to fill them all up with something to do. And then this here needs to have some ready for the next shot. So I need that number of messages again. Plus I need a couple more. That is how many messages I should ask for when I start up. And the system initializer will say, give me that number. And it will say, wham. Okay. And basically it's like breathing. These guys will go, pa-chomp, they'll do their thing, and it reads the next set. Pa-chomp, it reads the next set. And you never want to have any of these go to 0. So that's a simple computation to make. And if you approach it that way, this is a simple problem. And that's basically the essence of how queuing theory works. And there's a lot of math you can do, but it comes down to something as, that elemental. So here's a couple patterns that will help you work with actors. There's only, I think, 2, that's why there are a couple. They're very helpful, and they're buried in the Akka.pattern package. You could fuss around for a long time until you happen to stumble across these. So stumble over there first. So ask is the first one. Let's say I have a main program. I want to invoke an actor, have the actor do something, and watch for a result. When the result comes back, I'm happy. Now, an actor, as you've seen, can be the front end to a whole hierarchy of actors doing a whole lot of things. Remember the last slide I showed you? There was one actor that took incoming work, it fed it to a chunker, which then had an array of workers, which then gave us the result. So as far as we know, we're sending a message to one actor, but who knows what's happening behind the scenes, right? So I could just say ask, which is Akka pattern ask. Ask this worker, pass it a message to do something. I'm willing to wait up to this long, and when I get the result, something happened. I either got a result or I didn't. Now you can stop. This is actually the pattern up to there, that first line. That in itself is useful. We can go further, and this is that flow. We could say, I want to take the request and the result that I got before, and then I want to do something else with that, something greater, I don't know what, stir well, and then take that result and send that message, send it as a message to another actor. So that means my main program, which has no actors built into it, is communicating with other actors and getting results back. This is a problem you'll find when you're trying to design a program that uses actors. Think, okay, once I've introduced an actor, it can only talk to other actors. But at some point, I need to get the answer back to my main program. How do I do that? Well, this is one way. I have to say, I scratched my head over that question a lot when it first got started. So this is dataflow. You don't have to use dataflow, but it's available. So here's a way to take the result of a future and pipe it to an actor. So a future is a computation, it runs for a while, and the answer is available. Send that as a message to an actor. It's pretty simple. Create a future. Here's my callable. So in Scala, if you have a method and you just pass it in as a parameter, it gets wrapped into a callable, if you will. It's a closure. And it becomes a lambda, an anonymous function. And so this little method, we just pass it a method, it gets wrapped into a callable, if you will, and becomes a future, it's executed. When the answer is available, it gets sent to some actor. Very nice. There's an alternative syntax. We already have a future. You can do this. Finite state machines are available in Akka. They are implemented as actors. If you've done any network design, you know FSMs are all necessary. And the thing about that is FSMs are so difficult to create. And it's nice that that TypeSafe has given us that facility. but I wouldn't initially say, in order for me to do an FSM in Akka, I have to make the Akka FSM. You can, don't get stuck with that. There is FSM support available. It's done nicely. It is an actor. You end up debugging actors. So, I mean, here's an actual thing that I've been working on recently. It's a publish-subscribe system that uses 0MQ based on Akka, and it's got journaling with retry from subscribers, which can come up and down whenever they want. They can ask for replays of things. So then the response is narrowcast to them. And so this is just a typical kind of timeout. This is an FSM. I'm not going to explain it. But the point I'm trying to make here is draw the diagram. I mean, I've wasted so much time without the diagram. Now, testing actors can be challenging, especially when they're also needing dancing together, because actors are often not deterministic because they have shared state and they're interacting. Now, there was a wonderful test kit thing that TypeSafe has given us. What you need to know about that is that you need to provide a zero-R constructor for a Scala test. That was the main stumbling block. And then at that point, it's much easier. So I can tell that you're all dying here, and so I won't be much longer. I told you this was a long talk. Here's another bit of wisdom that I've learned the hard way. In a distributed system, this is probably the old-timers will nod their head on this one, time is relative. Each network node has its own view of time. Events happen with respect to its own view of time. And so not only are clocks skewed for every network node, but transmissions have jitter. And packets can arrive, cannot arrive. Akka guarantees that packets will arrive in order, but they are not guaranteed to arrive. So you may miss a packet, but never will you have them in the wrong order. They drop packets, however. So time, you can't trust time. And the other thing about it is if you're using the system clock for Akka, it's optimized for minimum resource consumption. It's not at all accurate. It seems to take it about 200 milliseconds. So if you want, what happens is every 200 milliseconds it says, gee, I wonder what events I should have sent out the door by now. And it sends them all at once. And then nothing happens again until the next system tick. So that's maybe not what you had in mind. And if you set a higher number, you would say, please do something every 50 milliseconds. It ain't gonna happen. Instead, every 200 milliseconds, you'll get 4 packets. So this is I put this up of the journaling broadcast system I've been working on, not because I want to sell it to you, but I wanted you to see that we have lots of different kinds of messages, and there's flows, and so it's starting to look like an operating system to me. I mean, you've got all kinds of messages going back and forth, and it gets really hard to keep track of. So I urge you to debug the diagram before you look at the code, because this is a lot more efficient. And then the test setup, I put more time into the test setup than I did the code, by a factor of 4 or 5. It's that much more difficult to test. Now I have a really cool test setup now, but it came with a great deal of pain. So one of the things about actors is that the wiring between them is done procedurally in your code. It's not like Spring, where you can wire things in a configuration file. So if you want to know what are the messages that are sent, you have to read all the code. You know when all the messages are received because you can go to the receive block and that's where they're all received. But you don't know where they're all sent from. So git grep is your friend, really. So I would think that if there's going to be a great leap forward, this is not on TypeSafe's roadmap, but if somebody wanted to make a name for themselves, this is probably it. In this world here, if you were to think of a Spring-like approach for declaratively defining which actors will receive what messages and do the routing, set up the routing that way. That would be a big step forward. Okay, so this subjected you to the end now, and I'm thinking of putting all this in another book. If you were going to read a book like this, would you be interested in the Java side of the story or just the Scala side? Thank you. And would you prefer to have just a few long examples that are carried through the book, or lots of little examples? The long examples? Little examples? Little examples? How many want the long examples? How many want the little examples? Littles have it. And would you be more interested in emphasis on distributed systems, or that is lots of network nodes talking to each other, or maximizing one big monster system? Distributed, okay. And what other software should the book talk about other than Akka in terms of interoperability? Nothing? Everything? Okay, I'm open to any other suggestions. Okay, so I'm done now. I have gone further than I expected. It's probably too late to show you any code examples. I have a whole lot of code examples. I could be here another hour or two, but I don't think there'd be anybody left. But I'll take questions now for starters and see where we're at. Questions? No questions. Is there any networking for jobs and stuff that you wanted to do before you ran out the door? Should I give away the prizes I promised?
Yes.
Yes, okay. Let's do that, and then if anybody wants to see code, you can come up and we'll talk about code. Apologies.